Swayam Prabha. Digital India. Educated India.
Last class what we did is we looked at a method called superposition method for handling beams subjected to uniformly distributed loads, and using one finite element we can get exact solution. As I mentioned, the problem with the finite element formulation that we developed is it gives exact solutions for displacements and rotations at the nodes, and so this gives accurate solutions for beams subjected to concentrated loads. And when beams subjected to distributed loads, when you apply this finite element formulation, it gives exact solutions of displacements and rotations at the nodes, but when you try to calculate moments, shear, or in fact displacement at any other point along the length of the beam, the solution may not be accurate. So one way of handling this is to increase the number of finite elements so that we approach the exact solution as we increase the number of elements, but that is not smart way of doing. The other way of handling this situation is you use a method what is called superposition method, which we discussed in the last class, and I want to just highlight what we have done in superposition method. In superposition method, the solution procedure is like this. We can write the element equations and assemble the element equations to get the global equations and solve them in the usual manner. So if a continuous beam is given with distributed loads, you just proceed as you do regularly, that is, you assemble the global equations and based on element connectivity assemble you get the element equations, and based on element connectivity you assemble the global equations, and then you apply the boundary conditions and solve these equations and get the nodal values. So in superposition method up to that point it is same. After that, when you are calculating or when you are computing the element quantities, that is displacement at any point in an element using the nodal values, or moment at any point in an element, or shear at any point in an element using the nodal values, what you need to do is you superpose the exact solution of fixed end beam problem. Means imagine in this continuous beam each of this span is fixed, and you get the fixed end moment solutions and you superpose those on the solution that you got from finite elements. So that gives you the correction, that is the superposition of fixed end moments acts like a correction, and you will be able to get exact solution even with less number of elements, in fact even one element. So here it goes like this. So displacement at any point in the element, so the first term, here you have two terms. The first term is nothing but what you do by using the nodal values V1 theta 1 V2 theta 2, you interpolate using finite element shape functions. To that you are adding the second term. The second term is coming from fixed end solution, and fixed end this is the corresponding solution, fixed end solution corresponds to the problem of uniformly distributed load over the span. So this is the correction term, and if it is the second term is not, you will not be having this term if it is a point load problem, because you do not need to apply this correction term, and this formula is coming from superposition method. And next moment at any point, bending moment at any point in the element is as usual you can interpolate using the nodal values, and over that you superposed fixed end moment solution. Similarly for shear force at any point in the element is given by this one. The first term is nothing but interpolation of the nodal values as you do for any other problem with concentrated loads, and second term is the correction term for the distributed load case. And as I mentioned, all these correction terms here they are corresponding to uniformly distributed load, fixed beam with uniformly distributed load, and if you have some other loading you need to add the fixed end moments corresponding to that loading, imagining that the each span of the continuous beam is fixed. So now let us take an example and see, or we will take the same example as what we have seen earlier, that is uniformly distributed load, total beam, simply supported beam, uniformly distributed load, length of the beam is L, and earlier we solved using two finite elements, and we observed that the end shear and mid span moments they are not matching with the exact solution. And so then what we did is we started out discussing about the superposition method. So now let us go back to the same problem, and as I mentioned, even with one element solution you will be able to get exact even with one element you will be able to get exact solution. So let us see how it is possible using the superposition method. So this is a simply supported beam subjected to uniformly distributed load having span L and modulus of rigidity EI, it is constant. So we are assuming a prismatic beam and uniformly distributed load, and this entire beam is discretized using one element having length L, and the nodal degrees of freedom are V1 theta 1, V2 theta 2. So element solutions, you know there are no point loads or concentrated loads, so element solutions looks like this. And now since we use only one element, this also becomes a global equation, and now we need to apply the displacement boundary conditions. Displacement boundary conditions here are: node 1 is fixed in the transverse direction, node 2 is also fixed in the transverse direction. Sorry, it is not fixed, actually displacement in the transverse direction is restrained. So V1 is 0, V2 is 0. So wherever essential boundary conditions are 0, reactions will be developed at those locations, and so we get this equation system substituting V1 is equal to 0, V2 is equal to 0, and the corresponding locations in the force vector are replaced with reaction R1 and reaction R2, and since V1 and V2 are 0, we can eliminate rows and columns corresponding to those locations. So we can eliminate 1 and 3 rows and columns, and we get the reduced equation system by eliminating 1 and 3 rows and columns, which we can solve for theta 1 and theta 2, and the solution is this one. And now since we got all the nodal values, that is we know what is V1, and now we calculated theta 1. Similarly we know what is V2, and now we calculated theta 2. Now we are ready to solve for the element quantities. So displacement, element quantities like displacement at any point in the element, moment at any point in the element, shear at any point in the element. So displacement at any point in the element using these nodal values V1 theta 1, V2 theta 2. We can interpolate using finite element shape functions, and the first term is nothing but interpolation of using finite element shape functions, and the second term is coming from fixed end moment displacement. And these fixed end moment values can be obtained readily in any of the elementary strength of materials or mechanics of materials books. And now we have the nodal values and also we know the correction term. So, we can simplify this further and we get this one. And if you want mid span displacement, since we have taken only one element, we need to substitute S is equal to 0.5. Mid span displacement we evaluated at S is equal to half, that is 0.5 is this one. Please remember this value we got after applying the fixed end moment correction, and if we miss that correction term, this may not be the value that we will be getting, and this is the exact solution. And now bending moment at any point using the nodal values and second derivative of shape functions using or interpolating using the second derivative of shape functions and the nodal values, we will get the first term, and the second term is nothing but it is coming from fixed end solution, which acts like a correction term. And now simplifying this, and since we are interested or in the maximum bending moment, because last time when we did the comparisons between the solution that we got from finite elements using two elements and the exact solution, what we did is we compared mid span displacement or mid span moments and end shear. So, maximum moment is going to occur at mid span, and mid span moment is obtained by substituting S is equal to again 0.5, and that is sorry, this is M moment expression simplified. Now, maximum bending moment occurs at the mid span, which is obtained by substituting S is equal to half, and we get this value, which now matches with exact solution because we applied fixed end moment correction. Again shear at any point, and substituting the nodal values V1 theta 1, V2 theta 2, we get this one. Again first term is nothing but it consists of third derivative of shape functions and the nodal values, and the second term is nothing but fixed end solution for uniformly distributed load case, and once we apply this correction term we get shear like this, and shear at ends of the span we get by substituting S is equal to 0 or S is equal to 1. So, maximum shear is at the end and can be obtained by setting S is equal to 0 in the previous or in the equation for shear force, and we get the value minus QL over 2, and which now matches with exact solution. So, once again I want to emphasize that the effect of this superposition method is proceed in the usual manner of writing element equations, assemble them to get the global equations and solve for the nodal unknowns, and then when you are calculating, when computing the element quantities, the exact solution of fixed end beam problem is added to the finite element solution. So, this is the procedure. So, which we verified by taking simply supported beam subjected to uniformly distributed load, and we checked that with exact solution they are matching. When we apply the superposition method, the same problem when we solved with the two finite elements, there is some inaccuracy, and one way of handling it is to increase the number of elements, but that is not smart way of doing things. So, we will be adopting superposition methods whenever we have distributed load in any span of a beam. So, now let us take an example, 3 span continuous beam, find deflection, moments and shears in a continuous beam shown in figure, and the material properties, Young's modulus and cross sectional properties, second moment of inertia or moment of inertia are given, all are given in SI units. And earlier also we have seen similar kind of continuous beam, except that there we have point load at the middle of the mid span. We have a point load earlier of 8 kilonewton at a location which is middle of mid span. So, now only difference is in the mid span we have distributed load of 20 kilonewton per mm, and similar to what we did earlier, what we can do is, since this problem is symmetric with respect to the midpoint, so we can take we can use symmetry, or we can take advantage of symmetry of this problem and only model half of this continuous beam. And please note that at this supports the transverse displacement is 0, and also at the mid span, the rotation is 0 at the middle of mid span, sorry. So, using symmetry only half of the beam can be modeled, and the 2 element model looks like this, and in the half model, half of that continuous 3 span continuous beam model, when you take half of that, in the first span, or we have actually, if you look at this half model, we have 3 supports. So, we use nodes at each one at each support, and we get minimum we can use is 2 elements, and the displacements restraints are shown here in the half model, and similar kind of exercise we already did for this kind of 3 span continuous beam earlier with a point load. And so, the first elements the degrees of freedom are V1 theta 1 V2 theta 2, second element degrees of freedom are V2 theta 2 V3 theta 3. The global stiffness matrix for this example is similar to the global stiffness matrix for 3 span continuous beam we have seen earlier subjected to point load. Stiffness matrix remains same because span is same, and also material properties and cross sectional properties are same. Only difference will be the load vector or equivalent nodal load vector, because earlier we had a point load and now we have a distributed load. So, what we will do is, since we already solved this kind of problem, we will take the stiffness matrices from the previous calculations, and now let us concentrate only on the global load vector or equivalent load vector for each of the element and assemble the global load vector. And if you see element 1, there is no load applied, or in the span first span of 400 millimeters there is no load applied. So, load vector for element 1 is going to be this, and load vector for element 2, element 2 is having a distributed load of 20 kilonewton per millimeter, and also the span of this second element or length of second element is 200 millimeters. So, the load vector for element 2 we can obtain by substituting into the formula that we developed for the case of uniformly distributed load. Please note that this formula is valid only if Q is constant, that is Q is uniformly distributed. So, since our case here Q is uniformly distributed, that is the value is 20 kilonewton per millimeter, we can directly use this formula, substitute Q is equal to 20 Newton per millimeter. So, substitute Q is equal to 20 Newton per millimeter, L is equal to 200 millimeters, and do the computations, we get this. So, the global load vector, and here we have 3 nodes, at each node we have 2 degrees of freedom, and element 1 contribution goes into 1, 2, 3, 4 locations of rows and columns, and element 2 contribution goes into 3, 4, 5, 6 rows and columns, or element 1 contribution goes into 1, 2, 3, 4 locations of the global force vector, and element 2 contribution goes into 3, 4, 5, 6 locations of the global force vector. So, we get global load vector from this element load vector. Also, please note that V1 is transverse displacement at node 1 is restrained, V1 is 0. Similarly, transverse displacement at node 2 is restrained, V2 is 0, and rotation, because of symmetry, rotation at node 3 is 0. So, at these corresponding locations in the global force vector or global load vector, reactions will be developed, which are denoted with R1, R2 and M3, and these we do not know now, we need to determine later. So, these are unknown reactions. So, we got the global load vector. As I mentioned, the global stiffness matrix for this problem, we can take it from the earlier when we solve this problem with point load, from there we can take it. So, the complete set of global equations looks like this, and now as usual eliminating the rows and columns corresponding to the degrees of freedom which are 0, we get the reduced equation system, using which we can solve for theta 1, theta 2 and V3. The 3 unknown displacements and rotations can be obtained from second, fourth and fifth equations by eliminating 1, 3 and 5 rows and columns. So, the solution, this is the reduced equation system, and solving this, and please note that rotations will be in radians and transverse displacement will be in millimeters. So, we got all the nodal values, V1 is 0, theta 1 just we calculated now, and V2 is 0, theta 2 is calculated, V3 is calculated whereas theta 3 is 0. So, now we are ready to go to each element and solve for element quantities. The bending moment, shear force in element 1, bending moment, shear force in element 2, since we got the nodal values, but only thing is on element 1 there is no load applied. So, we do not need to apply fixed end moment correction when we are calculating moments and shears in element 1, and whereas in element 2 distributed load is applied. So, when we are calculating moment and shear in element 2, we need to apply fixed end moment correction or fixed end moment and fixed end shear correction. So, element 1 using V1 theta 1, V2 theta 2, there is no correction here, and at left end moment is given by substituting S is equal to 0, and at right hand moment is given by substituting S is equal to 1. And shear, again no correction is required because there is no distributed load applied, or in fact there is no load on a span or element 1. Element 2, the first part is interpolation using finite element shape functions, second part is coming from fixed end moment correction. Here this fixed end moment value or this fixed end moment expression is corresponding to distributed load, that is fixed end beam subjected to distributed load. Only thing is it is mapped onto S coordinate system, where S is equal to 1 corresponds to the left hand and S is equal to 0 corresponds to the left hand, S is equal to 1 corresponds to the right hand, and the length, the total length of the beam, which is going to be the L is mapped onto S is equal total length in the S coordinate system equal to 1. And shear or at the left hand, now simplifying this moment, we get this, and now we can calculate what is the moment value for second element at left hand and at the right hand by substituting S is equal to 0 and S is equal to 1. And please note that we will be drawing the moment using these values, we can draw moment and shear diagrams for the entire half model. And shear for second element is given by this, again first term is finite element interpolation and second term is fixed end shear corresponding to a uniformly distributed load, and shear at left end of element 1, element 2 is given by S is equal to 0, at right end of element 2 is given by S is equal to 1, and left end corresponds to support 2 and right end corresponds to middle of the full model or middle of the mid span. So, now we have element 1 solution, element 2 solution, and also at any point inside in the element 1 or in element 2, we can, if somebody is interested in finding what is moment and shear, we can substitute corresponding S value and we can get the moment and shear at any point in any of these two elements 1 and 2. So, with this information we can plot bending moment and shear force diagrams. Element 1 is spanning from 0 to 400, element 2 spanning from 400 to 600. So, if you see this moment diagram, the how moment varies with respect to the span, that is x axis. On the x axis you have span, and along y axis you have moment. From x going from 0 to 400, that solution is obtained from element 1, and x going from 400 to 600, that solution is obtained from element 2. So, combining these two elements solutions, we get the complete moment diagram for half model, and the other half of the continuous beam will have similar kind of variation of moment with respect to the rest of the half. And shear force similarly, from x going from 0 to 400 is coming from, that value is coming from element 1, and 400 to 600 is coming from element 2. So, so far what we have done is we have concentrated on computing displacements, moments, bending moments, and shear forces for both kinds of loading, concentrated loads and also distributed loads. And now once we know these moments and shears, normal and shear stresses can also be calculated. So, now let us see how to calculate stresses in beams. Calculation of normal and shear stresses. Normal stress at a beam cross section is related to curvature by the equation given here, and please note that we already derived this equation when we are deriving governing equations for beam bending problem, using the assumptions of small deformation, and also using the assumption that plane sections remain plane after bending, and we obtain what is the transverse displacement value in terms of the displacement along the length of the beam value in terms of transverse displacement. U is equal to minus of y times second derivative of transverse displacement with respect to x. We obtained that, and using small deformation assumptions, we got from that displacement u, we got strain, and using Hooke's law, we related strain to stress through this material property Young's modulus, and that is how we got this equation. Normal stress at beam cross section is related to the curvature by sigma x is equal to minus E times E is Young's modulus, y is the distance from the neutral axis to distance from the neutral axis to the location where you are where you want to calculate the stress. And now we also know that the relationship between bending moment and curvature, m is equal to E I times second derivative of transverse displacement with respect to x. So, we can relate this stress to moment, bending moment, using moment curvature equation. We get sigma x is equal to minus of m times y divided by I. I is second moment of inertia or moment of inertia of cross section. So, whether it is concentrated load or distributed load, using finite elements we have seen how to calculate bending moments at any location in the beam. So, once we get bending moment at any location in the beam, we can use this equation and get the normal stress. And now let us look at shear stress computation, and computation of shear stress is more complicated and depends on shape of cross section. Shear stress can be computed or calculated by considering a free body diagram of infinitesimal segment of beam along its length direction and equating unbalanced normal forces to shear force. So, we will be drawing free body diagram, and this free body diagram is for a rectangular section with the depth of the beam as 2h and width of the beam is small b, and the small element dx various forces acting on that, normal forces are shown there. Sigma x is acting on left side and sigma x evaluated at x plus dx is acting on the right side. Now, considering equilibrium of forces, all forces are acting in the x direction. So, considering equilibrium of forces at a distance y from the neutral axis, we get this equation. So, this is what is mentioned earlier. The computation of shear stress is obtained by considering or by finding the unbalanced normal force and equating that to the shear force. Shear force is denoted with tau xy and b is the width of the beam and dx is this infinitesimal element that we are, the length of it we are considering, infinitesimal length, infinitesimal element length is dx, and so tau xy times b times dx gives shear force, and that shear force we are going to equate to unbalanced normal force. Normal force is obtained by multiplying sigma x with b and dy. Dy is small slice taken at a distance y from the neutral axis, thickness of small slice taken at a distance y from the neutral axis. So, sigma x times width times dy integrated from 2h, you note down here 2h is total depth of the beam and neutral axis is coinciding with x axis. So, h, the beam depth goes from h to minus h. So, integrating this sigma x times width times dy from y to h gives us normal force, and integrate it on either side of this infinitesimal element, we get what is shown there in that equation on the right hand side. And simplifying this equation by substituting what is sigma x we just learned that it is, or we have seen it is mi times mi divided by y, sorry it is sigma x is my divided by I with a negative sign. So, sigma x, substituting what is sigma x evaluated at x and sigma x evaluated at x plus dx, and also here the relationship between moment and shear is also used. We know that derivative of bending moment gives a shear force, so that is substituted, that value dm by dx is substituted as capital V. So, now we got what is sigma x evaluated at x, sigma x evaluated at x plus dx. So, now we can substitute these things into the equilibrium equation we have written by considering forces acting at a distance y from the neutral axis, and here capital M capital V are bending moment and shear force acting at the cross section. Substituting these in the equilibrium equation, we get this one by simplifying, and the stresses for other cross sections can be computed by following similar procedure. So, we learned how to calculate normal stress, we learned how to calculate shear stress, and normal stress is dependent on bending moment at any point along the length of the beam, and shear stress is dependent on shear force at any point along the length of the beam. So, once we calculate bending moment and shear force using finite elements, we can calculate normal stress and shear stress using these formulas or using these expressions. And now we will consider the case of thermal stresses in beams. So far we have considered only the mechanical loads, that is distributed loads and point loads, and now we will be seeing how to handle the thermal stresses, how to handle thermal stresses because of variation of temperatures. Consider a beam, element subjected to a temperature change that varies linearly throughout its depth, means you have one temperature at the top surface and another temperature at the bottom surface, and in this kind of situation the element will experience curvature, because the temperature there is a temperature change between bottom surface and top surface. This element is going to experience curvature, and curvature is given by, here the element is shown, and suppose the element this beam element, if it is restrained to undergo this deformation, fixed end moments will be developed. So, curvature is given by the element, the curvature which this element experiences is given by this, which depends on the change in the top surface, the temperature change at the top surface of the beam and temperature change at the bottom surface of the beam, and also coefficient of thermal expansion and also depth of the beam. Here h, please do not get confused this h with 2h earlier, this h is total depth, whereas earlier when we are deriving or for the equations for stresses, shear stresses, we used 2h to denote the depth of the beam. Here we used only h. And so this is what I just mentioned. And if the beam ends are prevented from rotation, so whenever there is a curvature, beam tries to undergo some rotation, a uniform moment which is constant along the beam span will be produced in the beam, and this moment is given by this one. This is fixed and moments because of a temperature. So, it is denoted with M, capital M subscript Ft, and we know curvature. So, curvature times modulus of rigidity gives us moment. These fixed end moments due to temperature changes are shown in the figure, and please note that the direction of these moments is such that they oppose the beam curvature, and whatever is shown in the figure, that corresponds to the case of top surface temperature is higher than bottom surface. Suppose if the top surface temperature is lower than bottom surface temperature, the direction of moments will be opposite to the way in beam is going to rotate, or it tries to oppose the curvature because of temperature. And please note that in both cases no shear force will be there, and with the fixed end moments, remainder analysis or remaining analysis is very similar to the distributed load, and equivalent nodal load vector is equal and opposite to the fixed end forces and moments. And these points I just mentioned now. And please note that this moment, the direction of moments is always in such a direction to oppose the beam curvature. Okay. And in both cases, whether the temperature of top surface is higher or lower, in both cases no shear stresses will be produced. So, now we know fixed end moments, and please note that equivalent nodal load vector, we have seen this when I am explaining to you the physical interpretation of equivalent nodal load vector. I mentioned that equivalent nodal vector is equal and opposite to the fixed end forces and moments. So, there are no shear forces, only moments are there, fixed end moments. So, equivalent nodal vector will be given by this one, using the sign convention that we adopted for nodal forces and moments. Nodal forces are 0 and nodal moments are coming from fixed end moment because of restraining the deformation of this beam element. And this is how, if there is a temperature change, this is how we can assemble the nodal equivalent nodal force vector, and stiffness is not going to, there is not going to be any difference in the way stiffness of beam element is calculated. So, after solving the nodal unknowns, the finite element quantities, that is once you solve the nodal unknowns V1 theta 1 V2 theta 2 for beam element, the finite element quantities like shear, bending moment and displacement, or displacement, bending moment, shear at any point in beam is obtained by superposition of fixed end solution as it is for distributed load problem. So, displacement at any point in element is given by the first part is nothing but interpolation of nodal values, and the second part is the correction coming from fixed end solution. Here fixed end solution is nothing but the beam is trying to undergo some curvature because of the temperature difference of the top surface and bottom surface, and it is restrained, and so we know how to calculate curvature and also moment, and this solution for fixed end solution for displacement is obtained by integrating curvature twice and substituting the value of displacement at s is equal to 0 and s is equal to 1 as 0, we get this fixed end solution. So, adding this fixed end solution to the finite element interpolated or finite element solution, we get accurate solution, where fixed end displacement terms comes from integrating curvature expression twice, evaluating constants of integration from condition of no displacement at the ends. So, this is what I mentioned, and bending moment at any point in the element, as usual solution obtained by finite element by interpolating using finite element shape functions. To that fixed end moment solution is added, and shear force at any point is given by this one, and here the fixed end correction is not appearing, because if you see the curvature expression, the curvature expression is independent of s. So, when you take one more time derivative of curvature, it is going to be 0. So, there is no correction for shear force because of this temperature or thermal stresses, and we will look at an example involving how to calculate the forces moments in a beam subjected to thermal stresses in the next class.